Hello, Dr. Mike here. I'm going to give you a quick primer about hexadecimal. So why are we talking about this? Well, this is really pointed for my digital forensics class. However, it is just a general video I can use in any of my classes. So it's a quick reference, and there's lots of other videos out there that get into how to actually convert hexadecimal to decimal to binary and so on. So I'm not going to redo those. What I want to do is talk about the aspects of hexadecimal and some of the things about it as it applies to, at least for forensics. So in the videos after this, we will be referring to these concepts, and you'll have this video to refer to for reference. So again, no surprise, everything in computing is stored as a 0 or 1. It's written to disk that way. Say disk, I mean SSD or spinning disk. So how do we see the data when we look at it? Well, we don't typically look at it as zeros and ones. We actually see it in hexadecimal. So first off, let's talk about some of the stuff we have here. This is referred to as binary, or it's called base 2. Now there are other ways we can view this data. As we know decimal, which is, we have 0 through 9, right? Which is decimal. Referred to as base 10. Of course, we know this as 1, 2, 3, 4, 5, and so on, our standard numbering system. There's some other ones out there, 0 through 7, which I'm not going to go to in this video, but we'll just talk about it. It's called octal. It's a base 7. And then we have a numbering system that consists of 0 through 9 and A through F. So this is referred to as hexadecimal. I'll refer to as hex here. I'll refer to as hex. And it's called a base 16 numbering system. So we're just going to talk about really the binary and how we see it in hexadecimal and vice versa. Now there's, again, plenty of material out there, how to do the actual manual calculations on that. I'm not going to go into that in this video. And of course, in reality, there's tools that do this for you. You plug in the decimal, you get the ASCII back. There's ASCII, hexadecimal ASCII converters, and so on. Even binary to ASCII converters. So there's plenty of tools to do that. But it's important to understand how it's written to disk in the terms of for forensics analysis. So let's take a look at that. All right. So you can see here is a snippet of what you might see in what's called as a hex editor or Hexdump. And you're going to see this a lot in forensics and a lot of different areas of computing, but really for forensics, this is how we view binary data. We're going to view it here in 2-digit hex numbers. And a lot of times they actually have, in this case, Wikipedia. It's the Wikipedia page here. You can see they actually have a conversion here directly for this rather than Hexdump. So a lot of times you don't even need to do it manually or using external tools. But again, we need to understand how this is written to disk and what it means. So let's go and just take an example here. First concept, of course, is how do we get ASCII from hex? So how is it stored this way? And why does it show up as 5769 and so on? Let's just go ahead and convert it here. So I'll just do a quick down conversion. So we'll take uppercase D, lowercase r, and uppercase M. Dr. M, right? No spaces here. We'll talk about that in a second. So if we look at, and there's a lot of references out there. We have reference here for, this is IBM ASCII to decimal, hexadecimal, octal, and binary tables. Plenty of these around you can find. If we convert this, we'll see that uppercase D is 44. So this D comes across as 44. And we have the R, which lowercase r, so it's important. It is case, how the cases are represented in our tables are different. So upper and lowercase, 72, and uppercase M. And you can see here it's 4D. So this is what you'll see written to disk, 44, 72, 4D. Now how does it, what does it actually represent? What the hex dump or hex editor is showing you is is taking this and actually splitting it into its binary form. So if we take a look at this table here, we'll see 4 is 0, 100. So 0, 100. Of course, the same one, 0, 100. And we got, of course, 7, which is 0, 1, 1, 1. And we got 2. And if you don't know the old joke about the t-shirt, I should have worn it for this video. There are only, 10 type of people in the world, 0, 0, 1, 0. Those that understand binary and those that don't. 2 types. So you can say it's 10, 111, 100, 100. Here are 4 again. Again, this is in binary. We have this as 0, 100. And we have D, which is 1101. Right, so that's how we have the conversion here. So these ASCII characters are stored this way in hex, which really represents the actual ones and zeros on the drive you can see here. So again, there's tons of tables here, and if we look at this, it's more than just numbers. We have, of course, special characters, we have spaces, end of file, markers, and so on, carriage returns, form feeds, backspaces, bells. You can see there's tons of stuff here. So basically, for all the normal character sets we have represented, even delete, we have some form of hexadecimal for that. So when we look at stuff written to disk, again, and I'm going to talk about this through the lens of looking at this through hex editor or Hexdump, which you will do in my forensics class several times. It depends how it's written, and then that's going to depend upon the architecture of the system. And that's referred to as endiness. So endiness is the order things are written, and this is going to depend upon the architecture. Most of the times, example, Intel or x86 architecture, I think, uses Little Endian, and Big Endian is used by other architectures. So it's important to know that, because if you want to read stuff in hex editor, you can see here, it's important to understand the endiness of our system. So let's take this for example. So what that means is we have something called Big Endian, which you can see here. I'll call it Big E, and then we have Little E, or Little Endian. Make that lowercase e. Okay. What endiness is referring to as the Endian, Big Endian, means if we were to, let's go ahead and just clear the board off here. As this data is written to disk, the address, where it puts the most significant bit, hence the starting bit, is determined either in Big Endian or Little Endian by either the lower address or the highest address on record. So, example is, if we're dealing with a system that's Big Endian, so I'll put BE here. Again, we're going to look at that. What was that? 44, 72, 4D. Look at our memory space. So let's say this is 0x 4 with a bunch of 4s, a 0. It's our first register. And of course, the next one is 0x 4 with a bunch of zeros. I'm not going to write those out. And then 0x 4. That's 2. So we have these three bits here. These 3 bytes, I should say, stored in on disk. This is our register for our disk here. And by the way, the 0x, that is sort of a sort of notation for hexadecimal. So you'll see that a lot. You'll see 0x, and you'll see a number after it. So if we were to write out in proper formation, proper format here, the Dr. Mike, it'd be 0x 44, and so on, 0x, 72, and 0x, that's a really bad 0x, 4D. So that's what 0x usually means hexadecimal. For now, though, I'm just going to write out just the actual 44, 72, and 4B. So with a big Indian system, the lowest bit gets the most significant bit here. So 44, 72, and 4B. With Little Endian, using the same registers, it's actually just basically written backwards. The least significant bit comes first. So in our case, 4B, 72, 44. So you sort of read it backwards. And you'll see this in labs through my courses. It will go through and show you how to read what direction. So these numbers are going to show up in different formats based on the Indianness of the system. So pretty important aspect there. Something to keep in mind with the hexadecimal. So again, I definitely go out and look at hexadecimal, decimal, and ASCII, and really you can sort of see it in these tables. A null, of course, is 0, it's 0, 0, 0, and then so on. And then here we have like the good old 2. Number 2 is 32, of course, is 11, 0, 0, 1, 0, 0, 0, 1, 0, and so on. So this is a pretty important concept. And really when it comes to, again, when you're looking at it here, so it's possible you will be reading this direction. If this was a Little Endian system, and byte was it 30, 31, 30, 31, 32, 34, 30. You land the bytes here, these last 4 bytes. So if they're important, let's say they're part of either file signature, or maybe they're the indicator for the type of the format for the disk, things like that, or it's the end of partition. It could be written backwards. So it actually could be 0A 7469. Now in this case, it looks like it's regularly big Endian, but I'm not sure here. Let's look at this. This is an example. So anyways, that's all. Just remember hexadecimal. Usually you'll see it start with a 0x, and it's going to be 0 through 9 and A through F. And we're going to break those into 2 bytes there, the A through F. So as you saw before, uppercase M is, of course, is 4D. So that's an example of that. And if that was around hexadecimal with the hexadecimal indicator there, we have 0x 4D. So that should do it. Again, if you still want to learn more about hexadecimal, you want to learn about how to actually convert it, definitely a lot of videos out there, probably way better than mine. They go into not just this, but also about how to actually do the mathematical conversions. In the context of our forensics class, just understand what you see in Hexdump, what it means. So it's hexadecimal, it could also, the Endianness could change how you read that. So that should about do it. Again, this is just a quick precursor here for future videos that will refer to hexadecimal, and you can always come back to this and watch it again. Hope this was helpful. Thank you.